Today's video is about the rational root theorem, and this is a tool that's going to help us figure out where we might have x-intercepts or zeros of polynomial functions and help us to find some other ways to factor them from what we've had before. Now, as we saw in class today, having a factored polynomial, it's pretty straightforward to tell where those x-intercepts are. So we'll start by looking at a factored polynomial and comparing it to what we get when we expand that polynomial out, and do a little comparison there to see how the rational root theorem works. So if we consider this polynomial here, we look and we should be able to tell based on what we did in class today that this factor is going to give us an x-intercept at 1/2. This x-intercept is going to give us, this factor is going to give us an x-intercept at -2 with multiplicity 2. And this factor is going to give us an x-intercept at 3. So again, that's 1/2, -2 with multiplicity 2, and at 3. And then let's take a look at the expanded form of this. I've done the multiplication out, and I'm not going to show you that work. And here we've got the polynomial multiplied out. So basically the point of the rational root theorem is to help us get from this here to this up here that will be easier to graph since we have x-intercepts there. Now what the rational root theorem tells us that all possible rational roots are going to look like some fraction p over q. And every root we have up above is a fraction, right? These ones are just over 1. And what the rational root theorem tells us is that every p is going to divide 12. So for example, 1, a numerator here, divides 12, -2 divides 12, and 3 divides 12. And the root theorem tells us that every q divides the leading coefficient, right? 2 divides 2, 1 divides 2, and 1 again divides 2. So every possible rational root of a polynomial is going to be a fraction p over q, where p divides the constant term and q divides the leading coefficient. So that's a little bit of a look at how it's working, and we'll do some examples where we go through starting with a function that looks like the lower one and come up with a function like one up above. And just to give you a little bit of insight into why this is working for those of you who care, all of my p's need to divide this constant term because they're going to come from these terms here all getting multiplied together to give me this term here. And the q's are coming from the leading coefficient because these things here are all multiplying together, giving me the leading coefficient. So that's a very brief version for why this works. So let's consider this polynomial. F of x is equal to x to the 4th minus 2x cubed minus 12x squared plus 18x plus 27. And we're going to try to factor this using the rational roots theorem. So we'll choose our p-values to be factors of the constant term. So factors of 27 include positive and -1, positive and -3, positive and -9, and positive and -27. And q will be factors of the leading coefficient, which is 1, so those are just plus or minus 1, making the rational roots just these p-values. These are my possible rational roots right here. And so we'll go through and I will try using different ones of these possible roots to see if any of them work as roots of this polynomial. And I'll do that using synthetic division. So I'll start out, we'll try 1. This is a guess and check process, so 1 seems as good a place to start as any. And we will do our synthetic division. And drop down the 1, and we'll go through this pretty quickly. And since the remainder is not 0, we know that that did not in fact work. So I'll try something next. Why don't I go ahead and try, let's try 3. And so as you can see, this is guess and check, so the problems I give you will need to be pretty straightforward so the time to do the calculations doesn't get too long. And let's see how 3 works out for us. And this one's looking good. Oops, except I made a mistake. And the remainder of 0 means that 3 was a root. This also tells me how to factor this polynomial. It tells me that, well, x minus 3 is a factor. I'm getting that from the fact that this worked. And then I know that what's left over is x cubed plus x squared minus 9x minus 9, and that piece is coming from right here. So every time that I do a division problem and I get a 0 remainder, I know one step in factoring the problem. Now, if I look at this carefully, I should actually see I don't need to do any more guess and check because that's actually factorable by grouping. So the remainder of the problem I can do without using the rational roots theorem. And I'll look and I'll say, okay, in this group my GCF is x squared times x plus 1. And in this group my GCF is negative 9 times x plus 1. So I'll have the first step in factoring by grouping here. Now this x minus 3 piece out here we can sort of ignore and just treat this as its own factoring problem, but make sure that x minus 3 comes along for the ride at every step. So we'll get x minus 3 times x squared minus 9 times x plus 1. And do make sure when you get down farther, right to here, we keep an eye out for things that can be factored further, like our difference of squares right here. So my final factoring then is going to be x minus 3 times x minus 3 times x plus 3 times x plus 1. This piece right here comes from the difference of squares factoring right here. And I see, looking at my complete factoring, that I've got roots of 3, 3, negative 3, and negative 1, all of which were possibilities that were listed up here. So the rational roots theorem is a way to get started factoring. At some point you're hopefully going to find in the factoring process that you get to a point where you can factor using other means and no longer have to guess and check with the rational roots theorem. Now at any stage, by the time you get down to a quadratic that needs to be factored, you've got the tools to do that without guess and check, whether it's using factoring by grouping or whether it's using the quadratic formula. So there's no need to use rational roots right to the bitter end. And we'll try one more example of this where the leading coefficient is not 1. Here we'll consider the polynomial g of x equals 3x cubed plus 7x squared minus 4. Again, we know that our p-values are all factors of the constant term, which is negative 4. So we've got plus or minus 1, plus or minus 2, and plus or minus 4. Q are all factors of the leading coefficient, which in this case is 3, so it's going to be plus or minus 1 and plus or minus 3, which means my possible roots, well, in this case I can have 1 over 1, so that's going to be plus or minus 1. I can have 2 over 1, which would be plus or minus 2. I can have 4 over 1, so plus or minus 4. Then I can go through again 1 and 3, so that's plus or minus 1/3. I'll have plus or minus 2/3, and plus or minus 4/3. So as we can see, when the leading coefficient's not 1, the number of possibilities for roots can grow pretty quickly. So again, I will keep these examples pretty straightforward for you. So here I'll start off by trying 1/3, because why not? And so I do 1/3, that's 3, 7, 0, don't forget that 0 there, negative 4. And the 3 comes down, that's 3, and that 3 times 1/3 is 1, that's 8, that's 8/3. Now I'm actually going to stop here. Anytime you're using a fraction here, and you end up getting fractions down here, that's a sign that you're not going to get a 0 remainder, so you can go ahead and stop as soon as that happens. And I will go ahead and try 2/3. Okay, so again, 3, 7, 0, negative 4, and I'll get 3, 2/3 times 3 is 2, that's 9, 6, that's 6, that's 4, and that's 0, so that actually worked. So I know that this factors then as x minus 2/3 times 3x squared plus 9x plus 6. Now here, I don't technically need to do this, but it's going to make my answer a lot easier to work with. I'm going to multiply part of this by 3 and divide the other part by 3. So if I'm multiplying by 3 and dividing by 3, I'm not really changing anything. I'm just going to change how it looks. So what I'm going to do is I'm going to multiply this piece times 3 here, and I'm going to divide this piece by 3 here. Notice that every term here is divisible by 3. So multiplying by 3 right here, well, 3 times x is 3x. 2/3 times 3 is 2, so I'll get 3x minus 2 times, and then dividing each of these by 3, I will get x squared plus 3x plus 2. So again, I've multiplied by 3 in one place, divided by 3 in another place, making no overall change. But now I see that this is something that looks like I know how to factor already. So I'll get 3x minus 2 times, well, here I need numbers that multiply to 2 and add to 3. Those are 2 and 1. And here we are factored completely. And this first term gives me an x-intercept of 2/3, which I had right here. This gives me a -2, which I had right here. And this gives me a -1, which I had right here. So all of my rational roots were in the original list, but I didn't need to use the rational roots theorem once I got here. I could just factor as I already knew how. So I think I'm going to call it off with those two examples, and I will give you a problem to prepare for class. And we're going to do a bunch more practicing with this, because I know there's a lot going on here. So please prepare the following problems for class for tomorrow. So please prepare the following two problems for class. For this first problem, all I'm asking you to do is list all of the possible rational roots for h of x. I'm not actually asking you to try any of them in factoring it. For the second one, I would like you to try to factor this completely. And I will give you the hint that you might want to start off with a root of -3. Should make the problem easier for you to get started. So please prepare those, and I will see you tomorrow.